Hello everybody, my name is Milan. I'm the author of Modern Fortran, Building Efficient Parallel Applications. It's a book by Manning Publications, and yeah, if you're here, you know you're in Manning's Twitch channel. Thank you, Manning, for hosting me. Okay, so in today's stream, I'm gonna basically guide you through live programming of simple yet functional wave physics simulation in Fortran. Okay, so before I start, first I want to point you to a recently developed community project around Fortran. So the URL is fortran-length.org, and basically this website aims to be the home of Fortran on the internet. So basically it describes what the language is about. You can read the latest news. There's a newsletter that comes out once a month. There's a Twitter feed. Then we have a mailing list that you can subscribe to. Usually that's where people post various news announcements and so on. There's also a discourse forum, which I'll show you just in a little bit. And of course the GitHub repositories of the projects. The community is pretty big already, so we started about 7 or 8 months now, and they've been over 24 contributors across projects. So the main projects are the Fortran Standard Library. So you may or may not know, but Fortran itself is a relatively small language. It doesn't have a comprehensive standard library. It has what we call intrinsic functions and subroutines and modules, so they come built into the language. They're available in the scope right away. Most of them you don't need to import or anything, they're just there, but they mostly focus on mathematical and array numerical operations, a little bit of a character string manipulation, but there's not much going on in terms of a comprehensive standard library like many other languages do, for example, like Python. So the Fortran Standard Library is an open source community project that aims to provide de facto standard library for Fortran. And I'm gonna show you its GitHub page right now. Okay, so basically on this page you can read more about it, the scope, how you can contribute, documentation. So right now there's a full API documentation for the standard library on stdlib.fortranlang.org. Okay, so back to projects. Then there's also the Fortran Package Manager, and I'll say a little bit more about it in a bit because I'm also gonna use it in this stream. And of course this website. So I mentioned the discourse earlier. So we started the Fortran discourse about 6 weeks ago. There's quite a few interesting discussions already on the forum. If you're interested in Fortran, learning more, if you want to ask for help, definitely check out Discourse, come here, ask a question, say hi, whatever you'd like. Okay, what else? Yeah, so I mentioned the community, so let me just show you here all the contributors that participate in the project so far are listed, and of course this page is only going to grow in time, but there's already so many contributors, and yeah, I welcome everybody interested in in Fortran and contributing to these open source projects to join and participate, even just by lurking and playing with the projects, experimenting, maybe improving documentations, and even contributing to the code. Why not? Okay, so today's stream. Okay, let's start. So we'll go completely from scratch. So right now I'm in VS Code. I only recently started using VS Code. Before that I used Atom. I used VI a lot in between for small stuff. But so far I like VS Code better than Atom. It performs better on my computer. They're fairly similar in terms of functionality, but really any editor that you're most comfortable with will work. What matters is that you have syntax highlighting for Fortran. That's pretty much, I think, the most important thing about an editor. And a compiler. Okay, so the most widely used and most easily available open source compiler for Fortran is Fortran. It's part of the GCC suite of compilers. So let me take you there. So Fortran is pretty easy to download and set up on your computer. So on Linux, it's basically available from your system package manager. If you're on Ubuntu or Debian, you'll be using apt. If you're on Fedora, CentOS, Red Hat, you'll be using yum or DNF to install Fortran. And okay, so much for Fortran. I think I don't want to say anything more about it before I actually start using it. Okay, so let's clean this. I was experimenting earlier. We want to start from scratch. And you'll see I have a few files here. A Python script that I'll use for plotting. Fortran is not that great for plotting, for graphics. It's certainly possible to plot. So there's interfaces to OpenGL, GTK, SDL from Fortran, so through them you can do graphics, but really for right now we just want to use the simplest solution imaginable. And yeah, this is just a very simple bare bones Python script that I'll use to plot. Don't worry about it right now. And I also have a few shell scripts that I'll just use for convenience to automate converting images to a movie and to batch run a sequence of operations. Okay, so let's start with our project. I mentioned earlier that I'm going to use the Fortran package manager to set up and run our little project. And so let me take you to Fortran package manager and FPM right now. So this is a pretty young project, and basically it aims to be both a package manager and a build system. And the number one problem that it aims to solve is the user experience. So installing, building your Fortran package, getting dependencies, all that, doing it by hand or writing your make files or CMake lists can be quite tedious, complicated, and sometimes just plain difficult for larger projects. And Fortran Package Manager aims to make that really easy. So I mentioned it's a very young project, but it's already quite capable. And I'm going to showcase in this stream how you can use it for your Fortran project. Okay, so what I'm going to do, I already have FPM set up on my machine, but I'm just going to go through the steps of installing it so that you know how to do it. Okay, so I'm just going to copy the URL from here. Let's pull up a terminal. Let's see where I am. Twitch. Okay, Tsunami, that's going to be the name of our project. Git clone, paste. So let's clone FPM. Now, to install it, you'll need Stack. So Stack is Haskell's package manager and build system, I guess. So in the README, there are easy instructions on how to set up Stack and then how to install FPM. So I'm just gonna, I already have Stack installed, so I won't worry about that right now. But to basically install FPM, I'm just gonna run stack install in FPM directory, and it will do its thing. Okay, building all executables for FPM. All right, 15 viewers. I'm happy. Okay, compile, build, compiling FPM. Almost there. Okay, so it looks like it's done. It says copied executables to home Milan.local bin. So my FPM went there. Let's look. Okay, yeah, we have FPM there. And so when you do this for the first time, make sure that where FPM is installed, that you set that directory to your path. I already did that. So I can confirm by doing which FPM that it's indeed that one. Okay. So now that I have FPM, I can get out of here and go to my project directory. Okay. So the key premise of FPM is that the user is not supposed to do any kind of complex setting up of the build system or management of the package. Instead, the user must structure their project in a specific directory structure and follow certain file name convention. So if you're familiar with Rust and Cargo, this philosophy is very similar to Cargo's, and indeed we used Cargo as an influence for FPM. Now I'm going to show you the guide. So at the bottom of the README page, there's the packaging guide. It's basically a short text that describes how to structure your application layout or library layout for FPM. And you'll see that here in the talk, there are example package layouts, and then we have single program, single module library, multi-module library, various scenarios that you can have for your package. And say if you go single program, it tells you what the structure, basically directory and file structure of your package should look like in order to build your package with FPM. It expects this fpm.toml, so that's basically a configuration file for FPM. And for the simplest scenario, fpm.toml can contain just one line. So let's start with that. Let's start an fpm.toml here. So I'm gonna do name equals name of my package, so that's gonna be Tsunami. So Tsunami is the running example in the book. Basically, it's a shallow water equations simulation. So for those of you less familiar with the physics of shallow water equations, so it's a very simple system of two equations for velocity or momentum and mass conservation, but basically it simulates an evolution of a wavy water surface. And to do that, it solves both velocity of the water and water surface elevation forward in time. So, okay, this is my FPM toml. I'm gonna save it. Now, let's look at what my project structure is supposed to be. So we're gonna have a directory called app and the main program in main.f90. Okay. So I tend to alternate between the terminal and the editor. I'm still not 100% used and comfortable with the VS Code, so I'm gonna alternate between the two, but we'll get it done anyhow. So let's start with the simplest, basically the most minimal Fortran program. So you open it with a program statement, and let's call this Tsunami and program. Okay, so anything in between these two lines is going to be the body of our program. Any Fortran program must have at least this program unit, and it has to have exactly one. If you're making a library, you can have just modules. You don't need to have a program. But if you're making an executable application, you're going to have a program, and this is analogous to, say, main in C, C++, Rust, and similar languages. Okay, let's print something. Hello, Twitch. Okay, so now assuming I set up everything correctly, I can build my project with FPM by just typing FPM build. Oh wait, I'm in the wrong directory. Let me back up. So now I'm in my top level directory. Let's try this again. FPM build. Okay, so let's see what happens. We ran FPM build and we got gfortran, and it says it built main.o in this directory and an executable here. So let's go and look to make sure they're there. App. Okay, main.o and Tsunami as we expected, so we can run this program directly. Hello Twitch, good as expected. But I actually am not going to be invoking my program like that every time I compile it, because now FPM actually allows us to build and run our program in one step, and that's by doing FPM run. So here I typed FPM run, and FPM knew exactly where to find the executable to run it. We got the output on the screen, and this is analogous to, again, Rust's package manager cargo. When you type cargo run, it does exactly that. Now let's change my program a little bit. Hello Twitch. And if I do FPM run again, FPM will notice that I changed my program, so it will rebuild it and it will run. Pretty cool. Okay, back to our water wave physics. Let's type out first sort of our statement of a problem. So we want to solve shallow water equations. Now let me take you back to the browser. So the Wikipedia page for shallow water equations has this cool animation that basically shows you what's the solution of the equations. And these are my equations. You'll notice that here I listed two steps. Step 1, linear 1D advection, and step 2, shallow water equations. So we're gonna work in order here. So linear 1D advection, basically it's a very simple equation that describes how an object or a fluid moves in space due to some advective velocity. So because we'll be solving for water height and velocity, here I kept the notation. We have partial derivative of h over t time. So that's basically change of water height in time. And this equation states that the water elevation will change in time due to a gradient in space of water elevation being advected by a velocity. So this velocity is basically, just think of a background flow that is moving an object with it. So say if you throw a twig or a leaf in a stream, water is going to carry it basically where the water goes. So this u here is the velocity of the water. And then h is an object, except that this also applies to fluids. So the same physical mechanism applies to fluid as well as objects. Now, the reason we'll go through steps and start by implementing this is that all the building blocks that we'll use in this more complex set of equations, we will implement to use for this one. And this is a very simple one, so it's a good example for us to make sure that all the building blocks are implemented correctly before we jump into a more complex solution. Okay, let's go back to our editor, and basically I'm just gonna type this out in the comment, sort of in code, pseudocode. So basically dh dt plus u times dh dx equals 0. So that's gonna be our equation, and let's see how we can solve this. Actually, we can solve this not solve it, but we can rearrange it in a programmable form even without writing any code. So if you're familiar with arithmetic, basically we're gonna do some arranging. We're gonna move u dh dx to the other side, so we have dh over dt equals minus u dh dx, and then dh equals minus u times dh dx times dt. And now basically we'll need to invoke sort of an approximation to these derivatives. And the most the simplest way to approximate continuous derivatives, which is, so this is going to be necessary in order for us to program it in code. As you probably know, computers can't computers don't solve equations. Computers add and multiply numbers. So we need to cast this equation in a form that the computer can understand. So recall that this dh is a change in h over time. So this is really h in the future minus h in the present, which equals minus u times dh dx times dt. So dt is going to be my time step. It has to be discrete in order for it to be programmable. And okay, for brevity, let's just call this n plus 1 next. So n plus 1 will refer to the next time step, and n will refer to the present time step. Now let's do the same and recast the spatial derivative. So to do that, we're just gonna express dh, but now because it's a gradient in space, we're gonna do h at I plus 1, which is the next adjacent cell in space, minus h at I, and then we're gonna divide it by the grid spacing. So we're gonna express our equations and the solution to these equations on a grid and in discrete time. Okay, and that's it. And basically, because we'll be solving in each step for h at n plus 1, our final step is to move this to the other side. Okay, so our code is gonna look somewhat like this, and probably this time we can get rid of these underscores to get closer to the Fortran indexing syntax, which I'll cover very soon. Okay, so we have now, just for brevity, I'll just keep the original equation and the final form. Okay, so let's declare some data. So Fortran is a statically typed and strongly typed programming language. This means that variable types are evaluated at compile time. This is in contrast to, say, Python, where variables and types are evaluated at runtime when you run the program. And also, unlike Python, where variables can change type during the execution of the program, in Fortran, when you declare a variable to be of certain type, it stays of the same type for the remainder of the program. So let's start by declaring some data, and I mentioned that we'll be working on a discrete grid in discrete time steps. So basically we'll be working on numerical arrays, one-dimensional arrays of certain grid size. So let's declare that grid size. And then we also have a finite number of time steps that we'll solve our equation over. So let's just call this number of time steps. I just want to give you a heads up. So I mentioned that this is a project that is the running example in the book. What we implement tonight may deviate a little bit from the book, so the code may not be the same. I'm kind of winging it in the stream, but if you want to sort of look up things, follow along, and work through this example on your own at a later time. So basically, Manning put out this free ebook, Exploring Modern Fortran Basics, which is basically chapters 2, 3, and 4 of the Modern Fortran book, and they're available for free. And chapters 2, 3, and 4 essentially cover developing of this running example in its serial implementation, so the non-parallel version. And in later chapters we get into parallel. And I just want to let you know that this free ebook is a really great way for you to take a look and get a taste for the book, to see if you like it before you commit to buying the full copy. So this is again, this is available for free. Okay, let's get back. I think I say okay a lot. So we have our grid size and number of time steps. They're both declared integer. And another important thing about Fortran that you should know right now is implicit none. So Fortran has this historical feature. It stems back from, so Fortran started in the late 50s at IBM. So it's one of the oldest high-level programming languages, but it's definitely the oldest high-level programming language that's still in use today. So essentially, Fortran is a language that was invented to let people not program in assembly, which was super tedious, as you can imagine. Now, for a long time, Fortran had implicit types, and basically before actual type declarations were introduced in Fortran, I think that was in maybe Fortran 66, all variables were typed basically implicitly, and they were typed depending on the first letter of the variable name. So by default, num time steps would be an integer, but grid size would be a real or a floating point number, simply because the implicit typing rules said that, I think, from A to H and from maybe R or P to Z, they're real variables, and from I, J, K, L, M, N, and similar are integers. So I think it was Fortran 90 that introduced implicit none, or maybe it was Fortran 77, I'm not sure. But basically, implicit none was introduced to the language so that the programmer can say, okay, I don't want any implicit typing. I want to explicitly declare my variable names. And okay, I'm gonna demonstrate to you why that is important right now. So let's say let's do okay, my mind is blanking right now, but the point is, implicit none allows the compiler to catch errors for you when you use variables that are not declared. The bottom line is, always use implicit none without exception. It's a good habit to have, and it's a minimal nuisance. So just do it. It will save you a lot of time debugging. Okay, so let's assign some values to these, and let's say grid size is gonna be 100. a simple round number, and we'll have, let's say, also 100 time steps. You know what? Let's do 10. Simpler. Small number. Okay. So now let's print them out. And because we'll initialize these, they're known ahead of time, so we're just going to encode these values in the source code directly. We can also declare them as parameter. So, oh gee, what happened here? I tried to use a VI shortcut inside VS Code, that's what happened. And I have VI bindings here, but maybe not everything is working correctly. Also, why is this color red? I'm not sure, but let's run this. Invalid character name. Invalid character in name at 1. Wait, what's invalid here? Ah, typo. Okay. Took me a while to spot it. Okay. Aha. So compiler says num time steps has no implicit type. Did you mean num tie steps? So actually this was a typo in my code. So let's fix that. Let's run it. Okay, and it printed 110 is the values of these parameters. Okay, let's keep going. So recall that to solve this, we're going to loop in time for a set number of time steps. So let's introduce our time step counter, maybe n. And now we're going to do n from 1 to num time steps, and do, and here now let's print n of num time steps. So far I didn't mention anything about this print star. Print star is essentially the simplest print statement. By Fortran, you can list any number of variables on the statement, comma separated. You can even put literals in there, and it basically uses a default compiler dependent programming. So print star is most useful for simple printouts. Okay, fpm run. So fpm by default also includes useful debugging and warning flags. So here the compiler warned me that, okay, grid size declared here is unused, so we haven't used it in the code, so we get a warning about that. That is fine. So now basically we looped for num time steps 10, and then in each iteration we basically printed our time step counter. Okay, so far so good, and this is the loop inside which we will be solving. our equation. Okay, so I mentioned we'll be solving for water height, which we can represent as an array to basically capture a range of water heights in space. So let's declare our first array, and this one is gonna be real. This is our second type now. So real, let's call this, just h is fine, could be height, could be water height. How you name your variables, this is really a matter of style. In general, it's good to be explicit and verbose because it adds clarity to your code. But there's also the alternative view that for code that maps directly to mathematical equations, it's okay, and it can be nice to name your variables after the mathematical concepts. And actually, you know, I was while writing the book, I was pretty torn between two styles, and I was using this the short form style where I'd name my variables u and h just after the variables in the equations. But I was curious about what was the take of people in general. So I did a Twitter poll, and there were about 400 responses to the poll, and about 60% of voters preferred the explicit and verbose form, and about 40% still like the short, concise one. I still kept the concise form in the book, and I'm going to use it in this stream as well, simply because then the code maps really nicely to the equation itself. Okay, so h is going to be an array, and to make it an array, we specify its size in parentheses. So now this declares h, which is a real or floating point array with num-grid size elements. That's going to be 100. Alternatively, you can also do, there's a more verbose form to this, and sometimes it may be more readable, and that is the dimension attribute, and then you just say h. So now this says that h is a real with attribute dimension. So the dimension basically says this is going to be an array and not just a scalar, and its size is going to be num-grid size. What makes it convenient about having the more verbose form dimension is that now you can just say h and u, and both h and u are going to be arrays of this size. Whereas then if I was listing multiple arrays here, I would have to type again num-grid size. Okay, for now I don't need a second array, so let's just keep this short form. So whenever I can, without it being super obfuscating, I prefer shorter code over more verbose. It's just a personal preference, matter of style. In any case, when you program, you'll develop your own style. So whatever works for you is best. Okay, so we have our array, and we can easily initialize all values to, say, if I want to initialize it to 0. This is important because when you just declare a variable, by default it's uninitialized. So you need to assign it a value after declaring it to do so. So we'll just initialize everything to 0, and what I'm gonna do is print and h. So we'll be solving for h inside the time stepping loop. And for now, I just want to print out the initial state. Notice that I actually haven't initialized n here. So let's also do n equals 0. Let's hide the terminal while I'm not using it. Okay. N equals 0. And let's comment this out. I only want to look at my basically my water height array. Run. Okay, error says explicit shaped array with non-constant bounds at how did this even slip by us? So I'm not supposed to be telling num-grid size, but grid size. Okay. By the way, I expect my viewers to catch errors like this and let me know in the stream chat. Okay. Okay, so this time around I got a bunch of zeros. This first 0 here is basically my initial time step. And then h are all these other values. Now if you put an array on a print statement, it's going to dump all the elements on the screen. And that's exactly what happened. So now let me run this again and store it into a text file. And why am I doing this? It's because I want to plot it. So let's just set up my plotting environment real quick. So if you work with Python, this will look familiar. Just bear with me. I'm going to set up a quick environment. I only need matplotlib for this script. Okay, source activate pip install matplotlib. Almost there. Okay, there's a newer pip. We don't care about that right now. Let's run this, and I'm gonna feed the output from my Fortran program to the Python script. It says plotting time step 0. Let's quickly look at this. We went to the other side. Okay, so this is the x-axis is my basically spatial index. The y-axis is my elevation, and this blue line is just my zero-valued water height array. Now, before we actually do anything with the equations, let's initialize h to some more meaningful shape. Perhaps the simplest right now is to just say that h in some part of the array, perhaps from 40 to 50, equals to 1. So now here in parentheses, I'm saying this is Fortran's array slicing syntax. Basically it says that all elements from 40 to 50 will be set to 1 and the rest will be 0. Let's run this again. Okay, so now you see there's some 1 values here. Good. Let's write it to what was the name of my image? Water height. Okay, so this quick image viewer keeps running away from the screen. Let me see if I have a better way to display this. Okay, so I'm just gonna be showing it in the browser. Okay, so this is basically a top hat shape. Now this confirms that I initialized my shape correctly, just as intended. So we have 0 everywhere except between indexes 40 and 50, where I have value of 1. Good. So I guess maybe now I can just... Good. So I'll be using this to display my image. Okay, so this worked, but let's set it to something more realistic. So something smoother that better resembles sort of to say wave. It won't be a wave just yet, but you'll get the idea. So what I want to do right now is set Gaussian or a bell-shaped curve to the water elevation, and to do that I'll need a spatial counter. And now we're gonna loop from 1 to grid size. So unlike this loop where I'm looping in time, here I'm looping in space. So I want to loop over each element of the array. And I want to set it to something. Each element will be... Okay, so the bell shape is an exponential with minus... What was it? So we want to have I minus, let's say 50. That's centered, square. So I want it squared because when I is 50, this is going to be 0, and then the exponent of 0 is 1. So my water height will be 1 when I is 50, but on either side it's going to exponentially decay. Okay, so let's see what that looks like. This minus number here is very important because that's what makes it decay and not explode. Okay, I got an error. X argument of exp intrinsic must be real or complex. Aha, okay. So basically I tried to pass an integer to the exponential function, and the function expects a real or complex. So there's a few different ways we could do this. We could explicitly convert it to a real by passing it to a conversion function, real. So basically you give an integer or a complex number to a real, and it gives you a real number with the same value, same decimal value to say. Okay, my thing ran, and now I'm gonna plot it. Aha! What happened here? So my plotting script broke because it could not convert string to float. Ah, I see what happened. See, I directed fpm run to my text file where I want my output to go, but because I changed the source file, fpm also built the code, so my my output file ended up with this log from fpm. We don't want that. So let me redo this again. Run out and let's plot it. And then let's refresh. Okay. So now basically I get a spike with a very sharp decay here. There's an easy way to fix this. And basically we're gonna put a factor here. We're gonna multiply, basically we want the exponential decay to be much, much weaker so that we get a broader form of the wave. So I'm just gonna multiply this by 0.01. Now that we're multiplying it with a float, we don't need explicit conversion. And here we touch on a feature of Fortran that can be treacherous, but if you understand well how it works, it's quite powerful, and that is that Fortran uses type coercion, or so-called mixed mode arithmetic, and that is, say, when you mix an integer and a real in the same expression. Say if you're multiplying a real number with an integer, the compiler will under the hood promote the integer to a real automatically and then yield a real result. So for that reason we don't need explicit typecasting. And now I don't want to make the same mistake of doing this. Okay, fpm run, let's redirect it, and let's plot. Now I can look at my browser. Okay, much better. So now we have this sort of seamount. Well, not really seamount. Seamount refers to something else. Seamount is a mountain on the ocean floor. But basically this is sort of a smooth bell-shaped perturbation of the water surface. Okay. Back to my code. Also now I want to automate my pipeline. So I had this script prepared so I can just run that every time I generate a new output. So we're gonna fpm build in a separate step to avoid getting the log of fpm into the text file. and then we're going to fpm run and redirect it into the text file. Then plot it, and then this other part will come later. That's for the movie. I don't need it now. So now if I just do run, it's gonna build the code, run it, and plot it, so I can go straight to the browser. Let's see how I can refresh from the keyboard. Okay, like this. Good. Same. Cool. Okay, so we initialized our water height field. Now notice that because I'm looping over all array elements and sending an explicit value to them, I don't need to initialize to 0 anymore, because I'm completely initializing it inside this loop. Let's remove this. Another thing I want to do is, rather than using literal values here, I'm going to set them as parameters, so that when I need them, then I can just change them at the declaration. So let's call this decay factor, and let's call this icenter. So icenter is the index at which my perturbation is going to be centered at. And let's say 50 real parameter. Same for decay. Let's set it to 0.01, and let's make sure our code does the same thing. Very good. Nothing changed. Good, good, good. Okay, so we set up our water height array, and now we can just go ahead with our solution. So now we're looking at our equation here. I'm just gonna copy this here inside the loop. Now this is already, I believe, valid Fortran code. What we have not set yet are these few of these parameters. So we have the background velocity, we have grid spacing, which we haven't set, and we have the time step. So we can set them all here. Let's do real parameter. Let's just say 1. dx 1 dt 1. So in the metric system, basically a velocity of 1 meter per second on a grid with grid spacing. So that's the distance between each element of the array. The distance is 1 meter, and the time step of 1 second that will iterate forward in time. So with num time steps of 10, our whole simulation duration is going to be for 10 seconds. Now here, if you want to be pedantic and accurate, because these are real numbers, you can do 1 dot to indicate a literal real number, or even more readable variant is 1.0. So let's do that. It's not necessary. By default, all Fortran compilers work with single precision real numbers, unless you explicitly declare it as double or higher precision. So let's just do this for readability. Okay. Now let's see. We're not going to be printing this anymore. Oh, by the way, there's a cool way to mark up your loops. Also, if branches in Fortran say if this loop has a special meaning, let's say initialization of water height, you can label this loop by saying, say, init colon, and then goes your loop, your do statement, and then here at the end do you say init. So this basically gives a name to your loop, so it helps readability. It's not super useful in single do loops, but when you have multiply nested loops, triply or 4 times nested do loops, it's actually quite useful to have these labels, because it tells you which end do corresponds to which do. And here I can do, say, integration or time loop. I think I used time loop in the book. Time loop. Okay. Backdoor equation. Okay, so main thing is we have declared H as a one-dimensional array, and that's 1D array in space. Notice that here the way that I express this, what was pseudocode, actually indexes it in time. So we don't want that because our indexing is really in space. So this H I plus 1 minus 8 minus 1. That's okay. But this we may just need to say HI and H of I. So in each iteration we'll be overriding each element. So basically at any single iteration we're only keeping the current one in memory, and when the next iteration goes it overwrites with a solution for the next time step. This is okay because we'll be storing it into the output into the file at every time step. So basically here outside of the loop I had the initial print statement, and now I'm going to have a print statement inside the time loop. And what else is missing here? Yeah, I actually need to loop in space here as well. So let's call it space loop. Space loop could be an ambient music track. 1, 2, grid size. Okay, so now I need to also finish it with space loop. Okay, so I'm looping over all elements of the array, and here I'm doing the finite difference in space. We're gonna hit an issue here because we're doing a difference between two neighbors. If I go from one end of the array to another, we'll inevitably go out of bounds. Let's see, I'm curious if the compiler will catch that. So this code should not run. Aha. Okay, this is very cool. So thanks to the pedantic warning flags by FPM, actually the compiler warns us array reference at 1, out of bounds 101 greater than 100, in loop beginning at 2. Okay, so that's very useful. The program will still run, so this is not an error. Language totally allows you to do this. So you need to be careful not to go out of bounds with your arrays. So the program still runs, and we get the initial state. Actually, this whole thing is the initial state. And I'm getting Fortran runtime error index 101 of dimension 1 of array h above upper bound of 100. And it even tells me where that error occurred. Row 32, column 39. Okay, I guess it pointed at the end of the parenthesis, but close enough. So to fix this, actually, we need to not go from the very end, but start from the second index, and then go to the end of the array. And actually, there's a very important property here about the algorithm itself and the way this spatial gradient stencil is arranged. So in finite difference, this is called first order upwind differencing. And for our equation and for this simple solution, it's actually quite important. This order of indexing is important in order for the algorithm to be numerically stable. Okay, let's run it again. Okay, it runs. And let's see what my output looks like. Fun enough, plotting results is much slower than computing the results. So now I have a bunch of files. I have an image for each time step. So let's see what it looks like. So I have it at time 0, and then we have at time step 0 we have a good initial shape, and then we have nothing afterwards, so that's not good. Okay, let's see where I made the error. Okay, at this point it's all good here, and then we enter the loop. Aha. Okay, here's what happens. As I loop from 2 to grid size, so basically my I goes 2, 3, 4, 5, 6, all the way to 100, I'm overriding each element with the solution of the finite difference from that element, but then in the next iteration I'm using that updated value in the finite difference. So we actually need to do the finite difference with the previous time level. So to do this, I'm gonna introduce a temporary array in which I'm gonna do dh equals let's see if it lets me copy it like this. Okay. dx. Okay, so now do 2 to grid size. And let's call this gradient. So it makes code a little bit more verbose to label your loops like this, but when you come back to the code 3 months later, it's actually much easier to understand what it does when you have labels and also comments. So recall you can comment your source code with exclamation marks. So anything following an exclamation mark is a comment in Fortran. Okay, DH, and then here we're going to replace this with DH. Okay, why was this important? So now we're calculating basically the gradient. Let's call this actually DH dx to be more precise. DH underscore dx. So now we're first computing just the gradient. And we're doing that because the gradient needs to be computed with water height values from the previous time step, or the current time step. And we're computing the gradient for the next time step. So now when we use these pre-computed values in this loop here, we should have no issues calculating our water height for the next time step. What else is missing? We didn't declare DH dx, so let's just do DH dx grid size. And also let's notice that we're going from 2 to grid size, so actually DH dx at index 1 is not initialized. So for now let's just do dh over dx of 1 to be 0, and then these other values we compute in the loop. Let's run it. Plotting. Update. Oh no, wait, that was just the initial step. All right, so Eureka, our shape is now moving to the right, and it's moving due to background velocity u. Now what I'm concerned about is what happens when it reaches the end, and that's basically a question of boundary conditions in partial differential equations. So boundary conditions, basically you need to tell the system that you're solving, or the program, what happens at the boundary to the solution. Does this quantity just leave the domain, or does it reflect back in, or is the value constant at the boundary, or does it appear from the other side? So in the book I do what's known as the periodic boundary conditions. So basically this amount would goes through this end of the plot, and it should reappear on this end. And let's do that. So to do this, I actually need to specify what's the value of dh dx at the first grid point. Because my form is moving from left to right, we're always updating the grid point on the right based on the grid point on the left. So we need to specify the boundary condition at the first index of the array. So instead of 0, actually, you know what? Before we do that, let's just see what the solution looks like as is, but I need to make a longer calculation. So let's do 100 time steps. And now, because the plotting is pretty slow, let's just not plot every time step, but let's plot every fifth. So basically this loop in my Python script plots for every time step, but now I'm gonna say if I'm not divisible, if my time step is not divisible by 5, I'm gonna skip. So only plot if we're divisible by 5. You know, actually now I realize probably it's fine. I don't care about refactoring this right now. And at the same time, because I want to see how this involves, now I'm going to enable my animation. So now the program ran for 100 time steps, and we're going to plot every fifth. So we should get 21 images. And I have a conversion script to MP4, and let's display this in the browser. Okay, so see what happens. We have our mount that just leaves, but nothing enters from the left. We actually want it to circulate. So it took it about 50 steps to leave, and actually the center reaches the edge exactly at time step 50. Seems like a coincidence, but this basically, we initialize our mount at the very center at index 50. We have 100 grid cells from one end to another, and in each step we advect the wave by 1 grid cell or by 1 meter. Let's see what happens if we decrease the velocity. Let's say 0.7. Actually, numerical properties of this algorithm dictate that the object will be exactly preserved in shape if the ratio of dx and dt is exactly u. But now u is smaller, so the algorithm should still be numerically stable, but our shape, I believe, will be deformed. So let's run it again and see what happens. I hope I saved the file before running it. Yeah, I think I did. Okay. Let's see what happens. Did I... Did this work? Oh, wait a second. What if I do 0.1? Run it again. Okay. So the deformation is more dramatic when I really lowered the velocity u. So now u is 0.1. So what that means is that the shape is moving 10 times slower than it did before. So in 100 steps, it only reaches grid point 60. But another thing that happens is, notice that this shape is sort of getting broader. Is getting lower and fatter. So that's basically numerical diffusion. It's a property of the algorithm. And as I mentioned before, for the algorithm to reproduce the exact solution, U must be equal to the dx over dt ratio. Okay, now back to our periodic boundary condition problem. Basically what we need to do is we need to assign it the value of a gradient at the boundary, and that's basically going to be this, except now because I is 1, I have 1, and this is I minus 1, so this can't be 0 because our array is not allocated over index 0. But this has to be now the end, the right side of the domain, because we want the shape to propagate through the right side and to come out from the left. So this is just going to be grid size. Okay. One aside here, so I mentioned our array is not defined over index 0. So by default, Fortran array indices start from 1. So for example, when you allocate or when you declare h to be of size grid size, its valid indices are from 1 to grid size. 0 is undefined. However, you can also do an arbitrary range. So you could define array to go from -20 to 50. And now this array its first index is going to be -20. And its elements are going to step forward all the way to 50 and are also going to include index 0. Okay, so I think we're good here. Let's run to see if our periodic boundary conditions worked. Oh, hey Andrea, I just see your message now. Ah, yes, single precision. Hello, Jason. Okay. So we ran, let's refresh. Not what I expected, so let's see where I messed up. So the gradient at the first point is going to be that, and then okay, I see what's happening. So we assigned the value of the gradient at index 1, but we still haven't calculated water elevation at index 1 because we're still looping it from 2 to grid size. So I also need to do h of 1 equals this. So we have a bit of code repetition here, that's fine. So this is still a work in progress. We'll have a chance to clean it up and really nicely refactor this at the end. Okay, let's make sure we save this and run it. So now I'm expecting to see my water to come up from the other side. Okay, great. So you see that now our wave is propagating through the end of the domain and coming out from the other side. So it worked. Very good. Okay, now notice this repetition in code that we have. So we calculate the gradient explicitly using the same formula at index 1 and then h1 at index 1. So that's basically needed just for the boundary conditions, and it just adds extra code unnecessarily. So let's try to refactor this a bit, and this is where I'll introduce whole array arithmetic. So basically whole array arithmetic in Fortran allows you to perform arithmetic over all elements of an array at once by simply applying operations directly to the array and not the individual elements. So what it means is that we can actually use index slicing here to do away with the loop. So let's see, dx, and we're gonna loop from 2 to grid size, and it's gonna be equal to grid size minus 1 to grid size. And in Fortran, similar to Python, if you're slicing from the very beginning of your array, you can omit the first index. So 1 to grid size is equivalent to this. Let's be explicit for now. And I should be able to replace this loop with this array form. And then we can do the same for the water height. Do the grid size. And you know what? Because evaluating h at index 1 actually has the same form as this. It doesn't need to be outside of the loop. So we could have placed as easily, yeah, so this was actually just this. And this is not possible because we're evaluating dh dx a priori. But that also means that now I can write my whole array arithmetic much simpler for H. So now, because we're going from 1 to grid size, which is the whole extent of my array, actually I don't need to slice the array at all. So I can do away with these. Okay, now this looks much better, much closer to our mathematical formulation. And let's run it to make sure I didn't mess anything up. Of course I did. Oh, wait, let's see. fpm build. See, another useful error message from the compiler. Shapes of operands are not conformable. So here I actually meant to type to grid size -1. So the two arrays are staggered and they must be the same shape. Let's make sure it builds. Okay, it builds. Let's run it and plot it to make sure that we get exactly the same result as before. Okay, good. Exactly as before. So now I can get rid of this, get rid of this. So now we have this special boundary condition, and we have our whole array evaluation of water height. So now our code is much simpler and shorter. But this boundary condition statement here is still pretty verbose and kind of ugly. So I think now is a good time to refactor this into a function. And to do this, I'll basically make a module to contain the function. Now FPM assumes modules to be in src, and I'm gonna call my source file mod diff f90. So now we have an empty file mod diff. And another assumption that FPM requires is that your module name is named the same way as the source file that it contains. So I name my source file mod diff, and my module is gonna be mod diff and module mod diff. Okay, so just like with program and recall that I did. So I had program statement, and here I have end program statement. Similar with module. So module statement has a module name, and then we finish it with end module. Technically, the language lets you just say end, so you don't need end module. It's perfectly valid code, but it's actually more readable to say end module. You also don't have to say the name of the module in the end module statement. I like to do so. I think it makes the code more readable, especially when your module becomes a bit bigger. It spans more than the size of your screen. So you actually, sometimes you're not sure, hey, which module does this end module statement belong to? So I'm just going to use it as a habit. Like before, we use implicit none. And so modules in Fortran are basically, it's a place where you can declare variables to be reused. You can define types in there. and you can define functions and subroutines in it. And then from the program, you can import functions, subroutines, variables from the module. So this module is gonna contain my function diff. So I'll call it diff. Basically, I'm implementing now a finite difference function. So I want to put this inside the function, and I also want to bake the boundary condition inside the function as well, so that actually here we can just do diff of x when our function is implemented. We haven't implemented it yet, so I'll keep this commented away for the time being, and this will take argument x, which is real. So now in defining the function statement, again, like with program and module, you just do end function diff to close it. You don't need to separately specify implicit none inside of function if it is defined in the module and you have implicit none at the top of your module. So as long as you always specify implicit none at the top of the module, you're all good with explicit typing in your function subroutines. Okay, function diff of x. Fortran functions and subroutines, when you declare arguments, you also specify intent. So intent in means that x is an input argument, it's not an output argument, and it can't be modified inside this function. So we'll do x, and we'll just put a colon here. So basically, putting a colon here for the array, for the argument inside the function, means that it will accept any size array. So if you pass it an array of 10 elements, it will work on that. If you pass it an array of 1,000 elements, same. So right now our function doesn't do anything yet, and let me just make sure that our flow works with FPM. So here I'm gonna do, actually before implicit none, we have the use statement. Use mod diff only diff. Okay, so I'm just gonna import this function. I'm not gonna do anything with it yet. The function doesn't do anything yet. It's an empty function. And let's see if we can build it and what that looks like. Okay, so we got a warning. No, we got an error. Contain function diff has no implicit type. Aha. Yes, exactly what the compiler is telling me, but I'm so used to kind of doing this on autopilot that it didn't click immediately. So because of implicit none, diff needs to be typed. So our input argument is real, and the result is going to be real. So we can specify directly in the function statement, or you can specify it in the body of the function. For example, it would be real diff and it would be size of x. But actually, you know what? I do need to specify it in the body because it's an array. The result is an array. So I need to do a real diff and basically the size of this the size of the result is going to be the size of the input argument. So let's see if that fixes it. Build warning, return value from diff not set. Okay, we expected to see that. That's fine. But see what happened now. So I just put a new module in SRC and I put the use statement in my main program, and FPM could on its own figure out that how to build the module and the program so that the program can use it. So now if we look at my build directory, we have so in the app it's still just the object file and the executable, and in Tsunami directory we have the static library which contains the module functions. We have the compiled module file. So this is something specific to Fortran, and these module files vary between compilers and compiler versions. But it's basically just an aid for the compiler in the process, and something you don't necessarily have to worry about it other than that they have to be generated by the same compiler. So you can't reuse a mod file from a different compiler. And this is the compiled object file. Okay, so this is pretty great. I didn't need to specify anything in FPM TOML for FPM to build this correctly. Now let's get back to our function. So I want to implement this inside a function, so I can just call it as diff. Oh wait, let's just do so actually I just want the finite difference here. I don't want to divide with dx yet, so I want to do that outside of the function. And we need to declare grid size, and grid size is going to be size of x. And then we're going to do diff at 1 is x, x. Here I'm just renaming the variable names, so they're inside a function, they're more generic. We don't necessarily want to associate them with any specific physical quantity. And now in my main program, I should be able to do just this. And if the output didn't change, that's going to be a good sign. But hold on, now I have an error. So in app main, diff of x, yeah, we want diff of h. Okay. Okay, so now we're not using dh over dh underscore dx anymore, and the compiler is correctly warning us about it. If the results are correct, we can clean it up. And it works, great. Okay, so let's enjoy the fruits of our labor by removing all this junk, and now we have this very nice single one-liner. We don't need this anymore. And that's it. So our program is now much simpler than when we were doing this in explicit loops. And if you follow the book or the free ebook, you'll see that I also abstract this initialization away in an external subroutine. So we won't do that in this stream in the interest of time. But I do want to, now that we have implemented this correctly, I want to go ahead and move forward to my step 2, where we'll solve the complete equations. There will be one important difference. So we're adding these additional terms, but now that we have implemented the gradient operator, del over del x, which is basically the diff function, now this is going to be much more straightforward to implement. So we'll be solving for 2 equations. I know it's getting late and we're almost out of time, so I'm gonna run through this fairly quickly. Okay, so beside h we'll also need u. So let's say this was our step 1, and now for step 2 we'll have 2 equations. So we'll have dh over dt. You know what, let me start with the velocity. So the velocity equation is u times du dx plus g over times dh over dx equals 0. H over dt plus d of h times u by dx equals 0. Okay, so this is basically the pseudocode form of these 2 equations. And I'm just going to describe what each term does. So recall our 1D advection equation, which just moved water in space without changing its shape. That term appears both in the velocity or momentum equation here. So this is the advection of velocity, but now because velocity is advected by itself, it becomes a nonlinear term, and that's going to introduce sort of a chaotic behavior in the flow. Chaotic just means that small initial perturbations grow quickly with time in nonlinear systems. So that's very common to, say, weather and ocean flows that are chaotic. And then this other term is basically the pressure gradient, or that's the work of gravitational acceleration on the water surface. So this says that velocity will increase more if the water surface is steeper. And this is pretty intuitive. If the water surface is pretty steep, the water will want to run in that direction very fast. If the slope is much gentler, the water will relax with a lower velocity. And then the continuity, our other equation, is basically just says that volume water has to be conserved. So when you have a velocity pushing into a focal area, there will have to be a compensating increase in water height at that spot. Similarly, if you have velocity pulling away, there will be a depression in the water height. So together, these two equations make up basically a simple 1D form of the shallow water equations. And this is the smallest set of equations that is needed to reproduce somewhat realistic water waves. Now, this doesn't include anything like forcing by wind on the water surface or internal dissipation, nothing like that. So it will just be kind of water sloshing around. Okay, so let's implement them real quick. Now our u won't be a scalar parameter anymore. It's gonna be an array, and we'll solve for it. We'll have to edit the time step to preserve stability, but we'll also need gravitational acceleration. So that is going to be 9.8. We'll revisit the value of time step in a bit. Let's keep the same initialization of our water height to a bell shape, and let's initialize u to 0. And now our equation, so I'm just gonna sort of copy this here for reference, and then I'm gonna implement it underneath. So u will be updated as minus u times diff of u divided by dx plus gravitational acceleration g times gravitational acceleration g times dh dx, so that's the water surface slope, and that's basically just going to be diff of h divided by dx. Good, I think that's it for velocity. And now for h, we're gonna have minus, so it's gonna be, you know what, let me save this for reference. Diff of h times u divided by dx times dt. We need times dt here as well. Now so far h has been just a sort of anomaly around 0, but we want to introduce some finite positive mean water depth, and that can be a scalar. Let's say real parameter. Let's call it depth. I think in the book maybe I call this h mean. I think depth is maybe more appropriate. And let's set it to 10 meters. So now we're going to have mean water depth of 10 meters. And any waves are going to be perturbations on top. And here we need to do depth plus h mean. But you know what? Now I realize that if depth is constant, then it doesn't matter inside the finite difference. So I don't think this will affect our solution. Okay. Okay, still 11 viewers. Good, very good. I'm happy to keep going, but we won't be too long. We're almost done. Okay, let's see if this builds first. Okay, it builds. Clear. FPM run. What does the output look like? Okay, we got a bunch of odd numbers, and that means my algorithm goes unstable. So recall that earlier I still use the same dx and dt, so my time step is still 1 second. But now I added all of these additional terms, additional physics to the set. So I actually need to greatly reduce my time step to preserve stability. So let's see if 0.1 is enough. Okay, still nada. Let's try 0.01. Okay, so it runs true. Without any NaN. So NaN is basically, it stands for not a number, and a variable gets a value of NaN when its value goes out of range. So when it's not anymore representable by the floating point model. So this can happen, say, if you divide something by 0, or if you perform an illegal numerical operation, it goes NaN. And NaN is a very common symptom of numerical instability in models. So now I believe in my book I had 0.2 seconds. Let's make sure that that still works. And now I'm going to run it for 1,000 time steps. So now with 1,000 time steps and 0.02 seconds time step, that means that my simulation is running for 20 seconds. Yeah. Okay. Still getting NaN. Let's go back to 0.01. Wait a second. Let's see. Did I mess anything up? This shouldn't be an issue, but also I don't think I need it, so let's remove that. Okay, let me see. u times diff u dt dx dt. Looks good. Okay, it crashes after a while. Let's go a little bit lower with time step. Really curious, so let me try to reproduce the solution from the book. So it's the same equations, u times diff u over dx plus g diff h over dx. You know what, we can refactor this. Let's get dx out of the parentheses. Did I initialize u? U is 0. Aha, you know what? I know what's the problem. I also need to update my algorithm. I forgot about this. So, recall I mentioned earlier that I'm using an upwind differencing. So upwind differencing worked well when we were moving something in one direction, from left to right, and we were differencing then backward from the current index to the back index. But now with these additional physics terms, we'll have water sloshing back and forth. So we have velocities going in both directions. So this algorithm actually becomes unstable for that situation. So I need a centered in space algorithm. And to do that, let's just real quick write another diff function, and this one is gonna be diff centered. Okay, it also takes x. Result is also going to be size of x. It's just that the differencing will be now across two grid points and centered in space. So I need to go from 2 to grid size minus 1. And that's going to be the difference between from 3 to grid size minus from 1 to grid size minus 2. Okay, and now I also need to adjust my boundary conditions. And now they need to be on both sides. So I need x at 2 minus x at the end divided by 2. And diff at grid size. Now because the flow will be going both ways, we need to specify boundary conditions on both ends. So diff at grid size is going to be x at 1 minus x at grid size minus 1 divided by 2. And I think this, so much for my function. So while we're at this, actually another useful thing to do in modules when you have multiple functions, and when you have functions that are meant to be for internal use only, and functions that are meant to be used by the user. So it's a good practice to declare everything as private. Private means that it can't be imported from outside the module. And then explicitly declare what's public. So we're going to have diff upwind and diff centered. And then now in main, I actually want to use diff centered. Now this little trick here is basically I'm renaming a function on import. So I'm saying I'm going to import diff centered and I'm going to call it diff. So now I can refer to diff centered with just diff in my main code. And now let's try this again. Function diff upwind. Okay, we get the error. Function result diff upwind has no implicit type. Aha, okay. Okay. So I declared it as diff, but now it's called diff upwind. There's an easy solution here, and you can add a result attribute to the function statement to just give it a short name to the result. So now I'm saying I'm going to refer to the result as diff, so this becomes valid. And I'm going to do the same here. Result diff. Okay. Nothing to change in main. Let's rebuild and run. Okay, we worked through all 1,000 time steps without hitting an NaN, numerical instability, which is good news. Notice that, so this actually ran pretty slow. And that's because, first of all, by default, FPM builds code in with all debug flags enabled, so no compute optimizations of any kind. And another thing is that we're printing the whole array to screen in every time step. So printing to screen will also slow down the execution. But with optimizations and without printing to screen, but perhaps writing to file directly, actually this runs blazing fast. So now let's try to go back and fix our time step. Can we run with 0.02 FPM run? No, I hit NaN, so let's try to go lower. 0.01. It's quite possible I still have a glitch somewhere. Perhaps in my finite differencing. Okay. P2. This all looks good to me. Okay, let's see what the output looks like. Sometimes that's just more informative than looking at numbers. So we'll have 1,000 time steps. I don't want to plot every time step. Actually, I'm gonna, you know what, I had it open here. So let's plot every 50th. And then I'm gonna do run. We're plotting and making a new movie now. And let's see what the output looks like. Okay, so what happens is that we have our initial bulge. It begins to depress as we go in time. So that's what we expect the gravity to act, to basically pull water down and to accelerate on either side. But as we accelerate, we develop these spurious oscillations. Now let's see if I can reproduce the parameters from the book exactly, because I know that one was stable. So that one used decay of 0.02. It was a bit sharper. Let's see if that will help. But otherwise, if not, I won't dwell too long on this. Often these kind of numerical issues are pretty difficult to diagnose. But the key point for this stream was really the Fortran implementation of the code. Still. So let's see what's different. You know what? You know, from the top of my head actually, so I don't think that it would matter, but maybe the depth parameter mattered here. And let's add depth and set it to 10 meters and run this again. I have the implementation from the book here on my other screen. You can see it. So I'm using it now because I'm running into issues. I'm using it for reference because I know that one runs correctly. Let's see if we can. Okay, a little bit better. So I still get these spurious oscillations, but at least I'm able to preserve roughly the shape of the wave. What happens with a longer time step should only make it worse, I think, but doesn't hurt to try. Okay, I expected to hit some NANs there, but didn't get them yet. Okay, I don't know what else to try here. So let me just double check this equation again. That looks good. Yeah, u times h. Okay. Let's make it a wrap here. So basically the end result is our wave. I still have some numerical issues here, but that's fine for one evening. I think pretty good, and I hope this gave you a nice flavor or a good taste of Fortran and how it can be used for numerical stuff. And I want to do one more thing, which is to show you a really cool feature of FPM before we wrap up. And that is basically how you can very easily include an external dependency in your Fortran project. And let me go back here to packaging. So Brad Richardson, the lead developer of the Haskell client, he recently added this capability which allows you to pull remote dependencies from GitHub automatically, or really any other publicly available Git repository. Dependencies. So let's see, where is that? Adding dependencies. Okay. So I'm going to show you how you can add a simple dependency in your Fortran project. So you'll have this block dependencies, and then you're going to specify git equals, was it git? Yeah, oh no, it's the name of the project, name of the package, and then equals curly braces and then git URL. So I'm going to pull my own datetime library. Basically it's going to be datetime equals git equals, and then we're going to do https github.com wavebit scientific datetime Fortran. So here you can also optionally specify tag, I believe, and if you don't, by default it will pull the code from master branch. And just for a demo, here I'm gonna say use datetime, I believe it's datetime module, only datetime. So datetime is basically a Fortran library that allows you to work with dates and times. Here I'm just going to use it for a demo to demonstrate. Type datetime is now. I'm going to use it to print the current time to screen. Print star now time. And then you can use the strf time format string to format your how you want your time to be output. This is somewhat similar to the ISO date format. And here I'm just gonna, because I'm doing this time demo, I'm just gonna stop here. So the stop statement will end the program right there. Now notice that I didn't put this module file anywhere in my project. I'm only including it here in the main program. And I only specified to FPM in its TOML file where to find datetime. and that should be good enough. So let's do fpm run, and now you see that fpm went and saw that I asked for datetime from this URL. It cloned the repository, it compiled it for me, and it made it available to my main program completely automatically, which is pretty amazing. And I'm personally really excited about this capability for Fortran development. We did get kind of an ugly output. Let's fix that. Let's see why that is. So, okay. So I didn't initialize my datetime instance now, and that's why I'm getting this sort of default value of datetime. So now equals datetime. Oh no, now equals now. So maybe actually now wasn't the best name for this. Let's call it current time, because now is the name of the method. It won't be an issue, so Fortran would still let you do it, but it's just ugly to call something now percentage now. Okay, let's rename this current time fpm run. All right, so I got my current local machine time in the terminal. I didn't have to get the library myself from GitHub. FPM did all that for me. It built it for me, and it took care of all the dependency handling for me. So this was very easy to, it's an easy way to incorporate a dependency into your project. Now, of course, it does require that the dependency itself is FPM enabled, that it has an FPM TOML package. I'm sorry, it has an FPM TOML file. So let me just show you what it looks like in datetime. Scientific datetime Fortran. So this is a recent addition. So you see FPM TOML is specified in the top level directory. And let's see what it looks like. So it has these this metadata stuff, name, version, license, blah blah blah, and it specifies how to build here, and basically the only thing here that needs to be explicitly specified is how to run tests for it, so that you can also, when you work with datetime directly, you can just do FPM test and it will run the test for you. But otherwise, this is it. Just this simple file allowed datetime to be included as an FPM dependency here. And okay, that being said, that's all, folks, for tonight. I'm looking forward to actually doing more streams. I'll probably start my own Twitch channel. So I'll keep you posted on it. If you don't know how to follow me, basically you can, let's see, probably my personal website is best. So yeah, on my personal website, my firstname.lastname.com, you can find my email at the end. Feel free to write, ask me any questions about the book, Fortran, or whatever. Definitely check out the Fortran Length website, and also I forgot to mention earlier, the Learn page will be home to various specific tutorials, which will be great for learning various aspects for Fortran. Right now we have this quick start Fortran tutorial where you can learn these basic features of the language directly on the website. There's also the compilers page with all the Fortran compilers, both open source and commercial. We looked at community, and there's also an index of packages on this page. So this is basically a registry of various Fortran libraries and tools that you can use for your work. Okay, last but not least, where was it? Yeah, so definitely if you're curious to learn more, take a look at this free ebook. It's a great way to get a taste about the full book, so you can see if you like the book before committing your money to buy the full copy. And of course, the full copy you can find at manning.com/books/modern-fortran. The book is finished. The third set of external peer review was done in February. Thank you to all my reviewers. They really made this book much better, and it wasn't an easy task writing this book, and it took a while. So thank you all who waited for a long time. And the book is currently in production, and we expect it in print sometime this fall. It was supposed to be this summer, but unfortunately due to the COVID situation, the production has been delayed. And with that being said, thank you all for tuning in, and I'll see you next time.